the balance of the root elements of a flat statically definable composite frame. So lesson number 218 of the book Mechanical Systems Calculations of the Marine Facilities. So we have to decide the exercise. The statically definable composite frame is assigned. The frame consists of three rods. The embedded rod 1 in the point A, AD rigidly connected with the rod DC, and hingedly connected with the rod CB, and the second support is sliding hinge. The composite frame loaded by the external load of P, force applied in the point D direct leftward, and distributed load Q on the rod DC downward, and the force applied in the point E. We have the hinge C and the force E, force F in the point E. The force directed perpendicular to the rod BC. Rod BC hingely connected in the point C, and the sliding hinge B sizes H is 5 meter, middle H, the point of the application to the force F at the H of 2.5 meter, and the horizontal size is 4 meter and 2 meter. So we have to use the balance equations of the parts of the composite frame or for the integral frame, and we usually just to remind that what kind of the methodic approaches we have to use. We have to make a choice first of the balance equation option. We have generally three options for the balance equation. Now, for the integral frame or for the separate parts of the frame, it depends on what efforts we search. We're searching the first option of the balance equation is equal to zero projections of forces on the axis. I just have to underline that we consider the flat state. So we are talking about the forces and the frame located on the plane. So plane have the coordinate systems of abscissa axis and ordinata. So 0, x, y generally. And the projections of all forces acting on the frame on the abscissa axis and the projection all forces on the ordinate axis have to be equal to 0 when we find the support reactions. One of two issues of the statics. I just want to remind that the issues are finding the support reactions of the mechanical systems and finding the efforts in the elements of the mechanical systems, and as well finding drawing up the balance equations. This and the third equation of the first option is the rotation moment of any arbitrary point. It can be around the point A, it can be any arbitrary point. For the balance have to be equal to 0 of all the moment of all efforts acting in efforts. I mean moment and distributed forces, concentrated forces, straightly directed left or upstairs, upward, leftward, or inclined. They all usually cause the rotating moment of in the mechanical system, and the moment according to the third equation of balance have to be equal to 0. Second form of the balance equation is that the total of moments of all efforts acting in the plane for the flat state have to be equal to 0 around the point A. It's arbitrary points, can be A, B, C, any points have to be equal, but just only these 3 points of rotation considered for second option of the balance equation. These all points of rotation would not be on the straight line, on one straight line. Third form of balance equation, it is that that the projection of forces on the definite one axis, it could be abscissa axis or ordinata. Here we have the abscissa axis have to be equal to 0. This one option, or this one condition of the balance of the mechanical system, and the rotation moment around 2 points, 2 rotation moments total around 2 points of all efforts acting on the mechanical system have to be equal to 0, point A and B. It's important for the third one. Condition is that restriction that the points A, B, and the axis 0x of the projection of all forces have not be perpendicular. I mean the segment AB and the axis of the projection of all forces. A little reminder of rules of projections of forces finding on the axis are indicated on the explanatory diagram on figure 2.18.2. So projections of forces we have to find of vector forces F and K. On the abscissa axis Fx and Px, Fx is the difference between the abscissa of the end of vector force and the beginning of vector force, and can be found by the magnitude of vector force multiplied by cosine of the angle of the inclination of the force relative to the abscissa axis. Or there as well for the second one force, the coordinate of end of force minus x, coordinate of the beginning of force, and due product of the magnitude of the force by cosine angle between abscissa axis and the force at the open angle. And this we have two adjacent angles, beta and gamma angle. The 180 degree minus beta equal to gamma. So on the other hand, we can find this projection as the magnitude of force by the cosine of the adjacent angle gamma. This is how to find the projections of forces. Just we can use this to decide the assignment. The rules finding algebraic moments of the force relative to the point. So if we have the mechanical body and the point of rotation, we have two forces. For example, here on the picture we have P, T, F, 3 forces. So algebraic moment of forces. In the plane we have algebraic moment of forces. When we consider the flat state of the balance of the mechanical system of body, this is for the flat state the rotation moment is algebraic magnitude. So algebraic moment forces F, T, and P are about the point A. Total of moment of all forces around point A is the total of moment of all forces around the point A is product of the force F. And we consider that F can be resultant of the set of forces. So it is just as total moment we indicate as sum of the moments of all components of the force F, as well as force T, total of all components, as well as force P. Could be the resultant of many components action with the resultant P, with this with T. So, and the product by the shortest distance between the line of the action of definite one force and the rotation point. And this distance satisfies on the perpendicular between the line of the action of force and the rotation point. Perpendicular. If a force line of the action crosses the point of rotation, the moment equal to 0, like here of the force P around the point A. Counterclockwise we assume as a positive, clockwise we assume as a negative. It's not so much important, but we can change these two moments in balance equation. Just do the equality to 0 of the moment. Finally, we can change the rules of the signs. Just multiply the left and right side of the balance equation. 0 multiply by -1. So the signs change it on the left side of the equation. 0 multiplied -1 remains 0. So the right side no change. So is the rule of science is appropriately relative. Just we have to remember that what sign rule we use in definite one case. Usually counterclockwise, these two forces like T and F rotate counterclockwise around the point A, watching from our side. From the other side, it can be clockwise rotation. So in these two moments are positive magnitude. And another one, we have to use the Varignon theorem of for the moment of the resultant force. And this means that moment of the resultant force here, for example, force F around any point of the figure, taken on the figure, inside the mechanical body shaded, or outside the mechanical body, it's not so much important. Any point can be, but the moment of force is equal to moment of components of force. Sometimes it's easy to find the arms for rotation moment for the components of force. Then the components of force, which are the projections of force on the coordinate axis, like in this definite one sample. For example, the moment relative to the point C of force F, what is? We on one hand, we can find the arm of rotation HC, but it could be also difficult, a little bit difficult, but we can go another way. Yeah, we can find it like size A is a diagonal of the right angle triangle, and we know that angle alpha equal the same time is in the right angle triangle CDA, etc. So we can consider last product of the DC, that is A, by cosine alpha. Yeah, we can do that, like here. But as well, we can consider the rotation moment as a action of two components of the force F. For example, the rotation around the point B, we have to use the A and the B plus C. So the rotation, we can decompose the resulting force F into two forces, F2 strokes and F1 stroke, and around the point B, the projection F stroke do not cause the rotation moment as this line of action of the component crosses the point B. So arm between the point B and the line of action of force F stroke is equal to 0. So we have only the arm B plus C for the F2 strokes component of the force phi or rotation moment around point B. Yeah, and first we have to determine the force component F2 stroke as product of force F by sine phi. A product force F by sine phi, we have the leg of right angle triangle, and this leg is here as well. And the force F is a diagonal of this triangle. And we have minus sign due to the force F2 strokes rotate around the point B at the clockwise. And the rotation moment around point A is minus phi on multiplied by HA. But we can consider this rotation moment consisting of two moments caused by two components of the resulting force F, where one component, horizontal one, is product of the magnitude of the force F by cosine alpha, the angle of inclination of the force F to the abscissa axis, and the force projection F2 strokes on the force F on the ordinate axis, vertical axis, is product of magnitude F by sine alpha. So this is just the reminds of the rules we use to decide the assigned issue to find the reaction in statically definable composite frame. Composite is because it consists of two parts connected in the hinge C. So we have one rigid angle D of connection of two rods of the frame, and another one, the connection is the hinge C. First, we have to define the a little bit more appropriate data. So first, we have to replace the distributed load Q by the concentrated load Q big letter. So this is distributed load multiplied by 4. 4 is the leg, DC, and we have H kilonewton. The BC, the diagonal, is equivalent to the length of the rod BC. We can find by Pythagoras theorem as square root of 2 sum 2 squared plus 5 squared is the sizes of the legs of the right angle triangle, equal to 5.39 meter. BC, CE is a and BE is a half of the diagonal, the right angle triangles, 2.69 meter. Cosine alpha is a proportion of GC divided by GC, one of the legs of right angle triangle, divided by the diagonal CB, and cosine alpha is 0.928, and the sine alpha is the is a fraction 2 by 5.39 equal to 0.371. So we have required geometric characteristic of the assigned frame and the concentrated force magnitude. And we next have to find the projections of force F on to use the Varignon theorem, finding the rotation moment around. We can probably use the Varignon theorem. And we first have to find the components of force as the projection, force F as the projections of force on the abscissa axis F stroke and on the ordinate axis Y F2 strokes. F stroke is the product magnitude F by cosine alpha, 6.5 kilonewton, and F2 stroke, the projection of the force F onto the ordinate axis, is product F by sine alpha is 2.6 kilonewton. So after that, we have to do the balance equations. First, we have to consider for the integral frame, the total of projection of forces on the abscissa axis, because we have here sliding hinge, so it don't cause a horizontal force. And we consider the horizontal component of force F. We have the external load P. It acts in the point A as the force of the reaction, horizontal projection of reaction axis. So we found that after the balance equation appropriate, we find that XA is P, the force applied to the point B, excuse me, apply point D to the left, and the horizontal component of force F minus F cosine alpha. Yeah, in the balance equation plus, but after mathematical transform with signs changes, so we have that horizontal reaction of the support for the composite frame statically definable is 9.5 kilonewton. After that, we consider the rotation of the this one rod CB around the point C. The rotation we consider of rotation moment had to be equal to 0 for the balance of the CB rod. So we we consider the force, this one force rotating clockwise with the arm EB, with arm EB is 269, and the force B and the force B relative point C is with arm 2, because arm is the shortest distance between line of the action of force and the rotation point. So we have that after mathematical transform, and we have that reaction of RB is minus 9.42 kilonewton. After that, we consider the left, or we consider the integral mechanical system of the total composite frame, that the projection of all forces on the applied axis have to be equal to 0, and the vertical axis we have projection of forces of YA is subject to find vertical direction in the embedding A, and minus QQ is concentrated force acting on the upper one rod, and we have plus F sine alpha is a component of projection on the vertical axis of the external load F on the rod CD, plus RB is direction got in the support B. And after the mathematical transform, we found that in substitute of the magnitude, so we found that the YA is vertical projection of the support direction, the point A, support direction force is 14.82 kilonewton. And after that, we do consider the total, the integral composite frame, statically definable, and for the balance, we have to find that when the all moments total action on the frame relative to the point A, this embedding of the left end of the frame have to be equal to 0, and this is subject to find the rotation moment of the support action MA minus assigned moment M plus P, the force on the left acting here, plus counterclockwise with arm 5 meter plus minus Q rotating clockwise with arm 4 divided by 2 is a 2 meter arm of the force Q relative to the point A, and plus the moments of two forces F stroke of two strokes. For F stroke, the arm is 2.5 meter. For F2 stroke, the arm is 5 meter due to it goes to the middle of the GL, the line of the action of this, and minus RB multiplied by 6, direction of the point B multiplied by 6 is the arm of the RB relative to the point A is 4 meter plus 2 meter. And after that, we can find the moment, rotating moment in the support action A is, after the mathematical transform and substitute of the magnitudes, equivalent to 15.77 kilonewton by meter. And as well, we can verify the equality to 0. We check moments of forces in the hinge C. So the hinge do not communicate and don't transmit the bending moments. So moments in the hinge have to be equal to 0 if only we have no the moment applied immediately right to the hinge. And we do not have this moment. And so the total of the moment rotating around the mechanical system of all assigned moment M, the reactive moment MA, moment of the force P do not act on the moment magnitude around the hinge C due to the arm of the line of the action of force P goes through the point C and do not have the arm. The force concentrated Q rotates counterclockwise with a positive sign around this force. We have the force F rotated counterclockwise with the leg with arm CE. We have the force RB rotating counterclockwise with the arm 2 meter. So after the substitute of all the listed magnitudes, we have that the total of the moments around the hinge C is minus 0.02 is about equal to 0 if you compare with other magnitudes. The 0.02 is right at 0, a very small magnitude. So questions and comments. Using balance conditions to find the support actions for composite frame. Yeah, we can consider the composite frame with the balance conditions. Balance conditions we have of usual three options. The first option is the equality to zero of three equations. First equation, the projections of all forces action on the integral frame or on the part of the frame. The projection of forces on the abscissa axis. Second have to be equal to zero. The second condition of the balance is the projections on the ordinate axis y of all forces action on the composite frame, and all moments, including the support reactions and the moment under the determination of the support reaction, have to be equal to zero relative any point. And the second option of the balance equation is that three moments of rotation of the mechanical system or its element around any 3 points, but these points have to not be on the same straight line. These moments have to be equal to zero. This second kind of the balance equation. The third kind is that the projections of all forces action in the system on one definite line could be any of the coordinate axis, abscissa ordinata, or it could be another line for the flat state, have to be equal to zero, and the totals of the moments around two considered points arbitrarily taken. But these points of rotation, the segment between 2 points, is not on the perpendicular line to the line of the projection of forces in the first equation of balance for third option. Finding the projection on the axis of the external force action on the frame, we use usually the cosine or sine function of the inclination of force to find the projection on the axis. But generally, the projection is in the vector approach is a difference of the coordinate of the end of vector of force minus the coordinate of beginning of vector of force. Using Varignon theorem to determine the moment of the resultant force as the sum of the moments of each component forces. Sometimes we feel difficulty to find the arm of rotation moment if for the arbitrary force inclined to the, if the force is inclined to the coordinate axis. So in this definite situation, we can consider the components of the force, which are the projection of the force on the abscissa and ordinate axis. And due to the Varignon theorem, the rotation moment of any around any point of the resultant force is equal to the total of components of this force around this point. This components, as we told, could be the projection of force on the coordinate axis, replacing a distributed load acting on a frame with a concentrated force. Yes, it's simple. Just if the force distributed even, so we just can find a product of the force magnitude distributed by the length of distribution. Sometimes if it other distributed, like for example, linearly distributed force, this is the product of the maximal magnitude of linearly distributed force. I mean that linearly in the triangle shape of distribution to the maximal magnitude of force within the distributed segment of rod. So the force is equal to 1/2 of product of the maximal magnitude of for the triangle distribution of force product by the magnitude of the segment of distribution of the force. Determination of support reactions in a composite frame using the balance equation. Balance, yeah, this is like in the first equation we have the three options of the balance equation to determine the support reactions. This is usually used for statically definable mechanical system, like considered frame. definable, statically definable, and composite frame connecting of two parts. But we as well can use a balance equation for the separate parts of the mechanical system, like for considered frame we did for two rigidly connected rods on the one hand, and for the hinged rod on another hand, we have the separate balance equation, all for the integral mechanical system. Checking the found support reaction using the equations of force balance and the hinge. Perhaps we usually can use the equality to zero of rotation moment of the forces around the point which one we did not use for finding of the support reactions. We have to find another arbitrary point. It could be the moment point. This reduces the action of all efforts in the equations, easy to calculate, or it can be the point of the intersection of the convergent forces. So thank you.